Assalamu alaikum. Dear learners, in this series of video lectures, I am going to start with the digital signal processing. In the previous lecture, I discussed that why we need signal processing when we are working with various instruments and measurement systems. The last lecture focused on analog signal processing techniques and the circuits that can implement the signal processing in the analog domain. I have discussed in that lecture that most of the systems which are being used nowadays are digital in nature. Therefore, we need techniques and ways to process the signals in digital domain as well. Therefore, in this lecture, I am going to introduce you to the digital signal processing, different components involved in the digital signal processing operations, and brief insight of the main interfacing components. I've talked about this thing in the previous lecture as well, that there are certain drawbacks associated with the digital signal processing methods. As the real world is analog, most of the components that we are using nowadays are producing analog signals. And if we want to process them digitally, then we need to convert those analog signals into digital ones. This conversion requires some time to be completed. Therefore, the digital signal processing techniques are inherently slower than the analog processing. And as we move from the analog domain into the digital domain, there are certain conversion errors involved. However, if we want to speed up the things and make sure that there are minimalistic errors affecting our signal, then we need to have more sophisticated equipment, which will increase the base cost of the digital signal processing equipment. Apart from these drawbacks, we will see that there are a number of advantages these digital techniques bring with them, ranging from the accuracy to ease of implementation and from integration-ready components to user-friendly and storage-friendly systems. A digital signal processing element consists primarily of two major instruments. The first one is the digital computer that will perform all the operations, and the second one is an analog to digital interface. This interface will be responsible for converting the signals from the real analog domain into the computerized digital domain, and then back from the digital domain to the analog domain if required. Whereas the digital computers will be responsible for performing all the operations which will depend on the software that is running on the computer. In such case, all you need to do is to modify the software of the computer to change the overall working of the digital signal processor. To start with the digital signal processing, you have to work on the basics as well. Whenever you will start to learn something about the digital signals, the first thing that will come into the mind is that how an analog signal will be converted into a digital signal. It will be out of scope of this course to discuss the basics of digital signals. Therefore, students should be familiar with the concepts of sampling, sampling frequency, Nyquist rate, aliasing, quantization, and quantization errors. This figure shows that if you convert an analog signal into a digital signal using a high sampling frequency, then this will be the curve that would represent the analog signal in the digital domain. You can see over here that how closely the samples are placed. Each dot over here is representing one sample. Therefore, you are getting a quite reasonable approximate of the analog signal in the digital domain. Whereas if you use a lower sampling frequency, that is, you will choose less number of samples in a unit second, then the analog signal will be represented by this curve in the digital domain. Over here you can see that the samples are coming after quite a while. That is, the first sample came somewhere over here, the next sample came over here, and then the next sample came at this time, and so on. So you can easily see that how this digital signal is not a representative of the analog signal. Moreover, you can easily see that how the digital domain has lost track of what is happening in the real analog domain, especially if you are using a low sampling frequency. There are many other considerations associated with this conversion, which I won't be going into the details of. For example, what is aliasing and how problems of analog domain can creep into the digital domain, what is quantization and what is associated quantization error. For an analog to digital converter, you have to hold the analog signal for at least the amount of time which is required by the converter to convert the signal into a digital domain. There are various forms of such a circuit that can hold the signal for some time so that the analog to digital converter can convert the signal into a digital form. One such sample and hold circuit is shown over here. The circuit is nothing but a voltage follower. If you close the switch S1, the capacitor will charge and apply a corresponding voltage at the non-inverting input of the operational amplifier. It is supposed that the switch S1 will be closed for a short interval during which the capacitor will get charged. Once the analog to digital converter has performed its task of conversion, the switch S2 will be closed to provide a discharging path for the capacitor. So, after the discharging of the capacitor, the switch S1 will close once again to hold the next value and the cycle will repeat. Once the signal is in the digital domain, now it's the turn of the software to do its magic. Any operation that was studied for analog signal processing can also be done in the digital domain, and that too with a relative ease. However, there is one catch over here. In digital domain, most of the processing is done in the frequency domain. Therefore, understanding of frequency domain is necessary for managing things in the digital domain. But as that won't be covered over here, I'll move on by making a simple relation between the generic equation of the linear time invariant system with the generic difference equation that governs everything in the digital domain. You must recall that when we studied the dynamic characteristics of the instruments, we saw this equation that related the inputs and the previous inputs to the current outputs and the previous outputs. Well, the digital form of this equation is quite similar, except for the difference that derivatives that were representing the previous inputs and outputs are replaced by previous samples. Therefore, x of n minus 1 over here represents the previous sample or the previous input in the digital domain. Similar correspondence may be established between other terms as well. Implementation of the difference equation in the digital domain requires the understanding of the Z-transform. The Fourier transform that you must have at least a slight idea of is just a special case of the Z-transform. The only thing over here I would like to explain is that how you can implement the difference equation and how you can represent it using a flow diagram. Let us write the difference equation represented by the flow diagram. However, before I start, the Z-inverse block represents the memory element that stores the previous values. So at this point, we will have y of n minus 1, that is the previous output, and over here you are going to have y of n minus 2. Similarly, over here you are going to have the previous input, that is x of n minus 1, and over here you are going to have x of n minus 2, that is the previous to previous sample. Using this information, writing the difference equation will become quite easy now. For example, over here you can see that this output is equal to whatever is coming out of this summation block. Now we have to figure out that what is coming out of this summation block. You can see that this term is entering this summation block, and from over here this term is entering this summation block. So we have to figure out these two terms. This term is quite easy. You can easily see that B naught is being multiplied with the input, that is x of n. So one term that is entering into this summation block is B naught multiplied with x of n. Secondly, now what about this term? This term is in turn a combination of multiple terms coming from these locations, and furthermore these terms are coming from these locations. So we will start from the bottom and go upwards. At the bottom we can see that there is the previous to previous output, that is y of n minus 2, multiplied with minus a2, a constant, It is being added into the previous to previous input, that is x of n minus 2 multiplied with b2. So the output term is going to have these two quantities. We can write them over here. We are going to have a b2 x of n minus 2 minus a2 y of n minus 2. These two terms will go up and they will be added with these two terms coming from these sides. Now what is coming from this side? From this side we are having a1 y of n minus 1, and from this side we are having b1 x of n minus 1. Now these three terms are going to add up over here, and then these three terms are going to go up and are going to add into this b naught of x of n. So at the end, all these three terms are going to add up. So if I can write the equation in a simple form over here, it would be something like this. That is, the output y of n would be equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 minus a1 y of n minus 1 minus a2 y of n minus 2. If you can take these two terms on the other side, the minus with the constants will become a positive sign, and you can say that you have jotted all the outputs on the left hand side and all the inputs at the right hand side. Now you can see that what is happening over here. The current output is nothing but a weighted sum of the current input and the previous inputs and the previous outputs. This is the same thing that was happening in the analog domain as well. However, over there we were using derivatives instead of these samples. So by just choosing different values of the constants, the operations can be modified. For example, for simple amplification and attenuation, only B naught will have a non-zero value while all other constants will have a zero value. For example, an amplification of 2 can easily be achieved by this equation, that is y of n equals to 2 times x of n. Now you can well imagine the difficulty you would have to face if you want to adjust the amplification factor if you are using an analog circuit. On the contrary, in the digital signal processing, you just have to change the constant over here to change the amplification factor. And that's it. Similarly, the constants of the difference equation can be adjusted to implement every kind of operation in the digital domain. Interested candidates are requested to consult digital signal processing literature for detailed explanation on how to implement digital signal processing methods. This was everything related to basics of digital signal processing from the mathematical and conceptual side. Keep on viewing the next videos for details of digital signal processing systems. Thank you.